Let's do a couple of examples of related rates problems. So this one comes from a multiple choice test that was released. I've been given here the volume of a cone based on its radius and height. You'll find that's pretty typical. You'll be expected to know the volume of a cylinder by heart, but for cones, spheres, other things like that, they'll typically give you the formula on the test. Here we know the radius and the height of this cone are both increasing at a constant rate of 1/2 of a centimeter per second. And the question is, what is the rate of change of the volume of the cone at the exact moment in time when the height is 9 centimeters and the radius is 6? So I'm going to start with figuring out what we know and what we're supposed to find. So they've asked us for the rate at which the volume of the cone is changing. That's the rate of change of the volume. That's dV dt. So that's what we're looking for. We seek dV dt at the moment described. And since we've been told how the radius and height are changing, specifically how they're both increasing, we know dr dt and dh dt. So our next job is to write an equation that relates V and R and H. And here, that's not the hard part because they've actually given us a formula for the volume of a cone. V equals 1/3 pi r squared h contains V and R and H. So I'm going to write that equation. I'm going to take the derivative of both sides with respect to time. So the part that makes this an interesting example is when I take the derivative of both sides of that equation with respect to time, I'm going to need to use the product rule. So you can see when I wrote it, I put a multiplication dot in between the r squared and the h. So do however you have to do to remember it, but we're going to need to use the product rule when we take the derivative. And we're also using implicit differentiation because we want to take the derivative of that equation, the derivative of both sides of that equation with respect to time, but time is not a variable in the equation. We have two other variables, radius and height. So I'm going to focus on the derivative of, I think of it as the derivative of the first times the second. And here you can kind of see, I use that dot to show you how I think of the first and the second. So this is the first. I'm going to take the derivative of that with respect to time and multiply it by the second. So here's my times h. So the 2 is going to come to the front. That exponent comes down to the front. The 1/3 was already there. The pi is a constant multiplier and stays there. My new exponent on r is 1 less. So my new exponent on r is 1. And then times dr dt because I'm taking the derivative of the first with respect to time, and time is not the variable that is in that expression. So this is the derivative of the first times the second plus this is going to be the first, so 1/3 pi r squared times the derivative of the second. Well, the derivative of h with respect to time is dh dt. So there's my product rule to take that derivative. And my job now is to freeze the picture. So now that I have an equation that relates dv dt, dr dt, and dh dt, I'm going to be able to substitute some of those values in. So especially here, I can't have used those numbers any earlier than this step that's coming up because then I'm taking the derivative essentially of a constant, which would be 0. So now that I've taken the derivative, I can use these values to substitute in. And since I'm substituting in, my expression is no longer for dv dt. It's dv dt at some specified moment. Here, it's not that this is any special notation, but to show that the place I'm freezing the picture is where the height is 9 and the radius is 6. So that's why I've used this notation. To just label that dv dt is not technically correct. So I've replaced my r with 6, my h with 9, and my dh dt and dr dt are both, in this case, 1/2. So just notice in the free response section, feel free to have stopped back at that last step. This is a multiple choice question, which this happened to be. We're going to have to simplify that enough to find a one number answer. So that simplifies down to 18 pi plus 6 pi, so 24 pi. We might, at some other problem, be asked about units. We were told what the units are going to be here, cubic centimeters per second, but we know anytime we find dV dt that we're going to have volume units divided by time units. There you go, 24 pi, cubic centimeters per second. I've got another example here. And to be frank, if you talk to some high school calculus students, at the end of the year, and you ask them, hey, what was the hardest part? They'll probably tell you it was related rates. But I'm going to tell you why. I don't think it's the implicit differentiation that's difficult. And every single related rates problem is an implicit differentiation problem. What's tricky is that this is an application problem. Every time related rates is an application problem, and it's my job to it's always going to be a word problem, because we were going to have this question about how is something changing compared to something else, right? So that's the tricky part, is the modeling, thinking about this scenario that's given in a bunch of words and trying to think of an equation you could write, a picture you could draw that relates those important variables. That's not a calculus problem. That's a modeling problem. So that's something we've practiced in other classes, and we're going to practice it more here. But that's what makes these problems, I think, seem scary to students. But I promise you, the calculus is straightforward. So I'm going to walk you through how I would think of this problem. If you're looking at all these words and feeling like, oh my gosh, I don't like it already, that's a normal reaction. You have lots of company, I'm sure, but we're going to walk through it, see what picture we can draw, see what sense we can make of this problem. So a police car is approaching a right angle intersection from the north, and it's chasing a speeding car that has now turned the corner and is headed east. Let's see what I'm going to think about. That's north, east, south, and west. Okay, I know at the exact moment the police car is 0.6 of a mile north of the intersection, and the car it's chasing is 0.8 miles east of the intersection. The police can tell how far apart the two cars are. Oh no, they can tell how fast the distance between the two cars is increasing. If I know at the same moment how fast the police car is driving, how fast is the speeding car driving? Okay, so what do we need to know? What do we already know? We know some distances. When it's time to freeze the picture, we know where we can freeze the police car and the speeding car. We do have one rate of change. Speed is a rate of change, right? It's a rate of change of distance. So the rate of change, the rate at which the distance is changing, and they tell us the distance specifically is increasing, is 20 miles per hour. So the thing is, I'm going to need to figure out how to relate the distance between the two cars to the distances I know, which are distances from some intersection. So I'm going to draw an intersection. I have a police car that's coming from the north. That means it's going south. And the speeder is going east, but has already turned the corner in this intersection. So headed toward the east, headed from the north. So at some point, the police car is like here, and the speeder is like here. And the thing that we know, probably because they have a radar gun, is the distance between them, which I'm going to show with this line, is getting longer, and it's getting longer at 20 miles per hour. So the idea here, once we kind of have this idea, oh, what picture did I just draw? And the distance between two things, but they're not driving in the same direction. They're, one is approaching a corner and one has already turned the corner. So I've drawn a right triangle. So I'm going to think about how I can use this right triangle picture to help me, number one, figure out what rates I already know and what rates I need to know, and write an equation that relates all of those things. So that was my reasoning through sort of my scenario. I'm going to change the slide now where I have a nice pretty picture, and we're going to figure out what we know and what we need to know. All right, so we have a police car going this way toward the intersection, a speeder going that way, away from the cops. They've already turned the corner and they're headed that way. And we know that this distance is increasing 20 miles per hour. So I'm going to give some names to some of the quantities, because that's what's missing from this problem for the first time. This is the first related rates problem where they haven't already implied the names of the variables. All there are is a description that says, I want to know how fast the speeder's going, but nobody's set me up a picture or drawn me, given me labels for those. So I'm just going to think of that as a right triangle. You might call that A, B, and C for A squared plus B squared equals C squared. I'm going to call this X for X distance, horizontal distance, Y for vertical distance. I'm going to call the side of this triangle Z. Well, the thing is, those three sides of that triangle are not staying still. They're changing. So I don't want to freeze the picture at, for example, 0.6 miles and 0.8 miles. Y and X are changing, so is Z changing. So, but now that I have this picture labeled, the thing I was supposed to find, what is the speed of the car? So that's how fast at what rate is this X distance getting bigger? Assuming it's getting bigger. It seems like it's getting bigger. Because the speeder wouldn't stop and go back toward the cop, right? So, how is this going to help us? We know dy dt because we know how fast the police officer is traveling. So dy dt is how fast y is, I'm assuming, is decreasing, right? Because the police officer is getting closer and closer to the intersection. So how fast is that distance between the police car and the intersection decreasing? And we know how fast the distance between the police and the speeder is increasing. That's 20 miles per hour. So we're going to use this. We're going to think of a way to write an equation that relates X and Y and Z. But I might have already accidentally said it, so you probably figured it out. All right, so there we go. If this is X, horizontal distance, Y, vertical distance, like north-south distance, and Z, and I know that has to be a right triangle, because this is a right angle intersection, then I know that X squared plus Y squared is going to equal Z squared. And now I've related X and Y and Z, which is the one thing I needed to be able to do. Now I know I'm going to take the derivative of both sides of that equation with respect to time. So just make sure that we use implicit differentiation. We're going to need the chain rule because time is not a variable in this equation. So when I take the derivative of x squared, I need to take the derivative of x squared with respect to x and then multiply by the missing piece, which in this case would be dx dt. So when I take that derivative, 2x dx dt plus 2y dy dt equals 2z dz dt. At this point, you might notice that you could divide that whole equation through by 2. Whether you did or not, it's up to you. This is an algebra problem now. And I'm going to be able to replace the things I know. So the really big important reason that this problem is in your practice, my examples, there's 2 reasons. Number 1, it was presented as a word problem with no variables. We had to start this from scratch and make our own picture. So that's going to be the place where you need to practice these kinds of problems. How can you take a big old word problem, sort of parse through it, figure out what's going on, get a handle on the situation, make a picture, write an equation. So we did it. We wrote an equation. It turned out it was the Pythagorean theorem, so it wasn't too bad. The other really important thing that we need to think about here is I made this claim at the beginning that we know dz dt, that's the rate at which the distance between the police officer and the speeder is increasing, and that's 20 miles per hour. I said also that we know dy dt, that's the rate of change of y. But you have to think about this. That distance y, and y is the distance, right? What's happening to it? It's getting smaller. It has to be getting smaller, and it's getting smaller at 60 miles per hour. So it's my job when I go to replace everything in this equation, except the one thing I don't know, the thing that I want to know. When it's time to replace dy dt, dy dt is negative 60 miles an hour because y is getting shorter, so dy dt must be negative. So let's just go through here. So this was supposed to be 2x. So in the line before, I took the derivative with respect to time. Now I can freeze the picture. I can use this x value that I know, 0.8 miles. I can use this y value that I know. And I can use, well, there's one other thing I'm missing, right? So let's just figure out where I got this. So this was my derivative, my equation where I've taken the derivative of both sides. The 2 times x times dx dt. X is 0.8 miles east. So once I freeze, this is 0.8. This is 0.6. Notice I haven't filled in dx dt because that's the thing I don't know. I'm not going to be able to plug in for that. I'm trying to isolate that to figure it out. Plus, this is supposed to be 2y dy dt. Well, once the picture's frozen, my y is 0.6. That's where this 0.6 came from. Negative 60, that's the big deal here, noticing that. I know the police officer is going 60 miles an hour. The police officer is getting closer and closer to that intersection, which means y is getting smaller, which means dy dt must be negative. And that's going to equal to, on the other side, so here's what I have. I have 2z dz dt. Well, the 2 is there. dz dt, I knew. I was told that distance is increasing, so it must be, the rate of change must be positive. And that's 20 miles per hour. How did I get this 1? So I have to think through, if I'm going to freeze this picture in time, and I know at that moment y is 0.6 and x is 0.8, I have to figure out what z is at that moment. I can use the Pythagorean theorem to find that distance z. So at the same moment when y is 0.6 and x is 0.8, z is exactly 1. That's where this 1 comes from. So now it's a matter of simplifying and trying to isolate the dx dt. So that 2 times 0.6 times negative 60 makes minus 72. On the right-hand side of the equation, the 2 times 1 times 20 makes 40. Here I have the 2 times 0.8 makes the 1.6. So I'm going to, I'm noticing a typo here. We're okay here. My next step would be add 72 to both sides, but it looks like I forgot to move that once I did. And I'm going to divide both sides by 1.6, so 112 divided by 1.6 makes 70. And I can find out that the speeder at that moment is going 70 miles per hour.